So today's topic, we're going to look at how do you add and subtract vectors. And it's really quite simple as far as the process of adding and subtracting vectors. So suppose you have those vectors, 5, 0, which is vector u there, and 4, 5, which is vector v. U plus v is the thought of you go in the direction of u first, and then you go in the direction of v afterwards. So what does that look like? Well, if you put them together, and there's sort of a, with vectors, there's sort of a head to tail kind of mentality. The arrowhead's on here. This is called the tail of a vector, and where it ends is called the head of a vector. So if you keep matching up, I ended here, so now I'm going to start my v vector and end up there. Then if this was my starting point, this will be where I end, and that will be the vector u plus v. So now if we look at our graph, what is u plus v? Well, we could count it out. How many more to the right do we go? Because that'll be our x-coordinate. How many up do we go? And we can write that out. Now, if you count it out, you've got 9 to the right and 5 up. And the interesting thing here in this diagram is it shows this that u plus v and v plus u mean the same thing. There are some things in math where that's not true. I mean, adding 2 plus 5, 5 plus 2, that adds to the same thing. But there are some things in math where if you switch them around, they don't add up or they don't multiply the same. But for us, it doesn't matter. And that property in math is called commutative. So if something can be rearranged and it's still the same thing, it's called commutative, and the order doesn't matter. Now, we could draw things out every single time and figure out that it would be 9i plus 5j. But if we look at the coordinates of our original two vectors, adding vectors is going to be really, really easy. So here's the column vector for the 5, 0 vector, and there's the column vector for the 4, 5 vector. How hard is it to add vectors? Not very hard at all. You're just going to add the corresponding coordinates. So 5 plus 4 is 9. And 0 plus 5 is 5. Subtracting vectors, exactly the same idea. If you wanted to do u minus v, well, you go in the u direction, and then minus v is the v direction backwards, right? Because v normally was this, right? That was normally v. So a negative v just means we're going in the opposite direction. So our blue one there, the resultant of subtracting u minus v. And again, how hard is it to actually subtract it? Not very hard at all. You just subtract corresponding coordinates. So here I'd like you to try this. You've got a vector A. It's written with the unit vectors. You can also write it with a column vector if you'd like. In fact, I find doing the math is going to always be easier with your column vectors. But draw each of these out. Draw A plus B. Draw B minus A. And the third one there that you can't see unless I show you an answer. And then I'll put the answers up in a bit. So I've always drawn the A vectors in blue, the B vectors in green, and then the resultant in red. Again, as far as putting your arrow points on, you have to think, where did I start and where did I end? And the drawing of the picture is really helpful in just seeing what's happening. But as far as doing the math, eventually you're just going to say, well, I know that A is 2, negative 1, and B is negative 1, 3. If I want to add those together, I'm going to get 1, 2, and that's a lot easier than actually having to draw things out. with these columns, things become really easy for adding and subtracting. And with numbers in front of vectors, like this 2p and minus 3q, that 2 multiplies every element of that vector. So the math itself isn't very hard. If you add them together, you'll get 1, -1, and 7. Here, if you put the half through first to see what happens to each of those coordinates and then subtract them, again, not very hard. Same thing with the last one. If you multiply by 2 and multiply through by that 3 and then subtract them, doing the math of adding vectors is pretty straightforward, which is what makes, partially what makes vectors so powerful is the math itself is quite simple. And then we can do some really neat things with those vectors, and we'll see that coming up. So I'll just draw a box over this for now. Well, that's a circle. One of the things that you can do to help yourself understand what's going on is to draw a little diagram. You know A to B, and you know B to C. Can you find A to C? So in other words, we want to find this one in red. And that vector in red is the same as if we wanted to start here and end here, we could do that in a number of different ways. We could go to B first and then go from B to C. We'll still start at A and end at C. And so if we take and go from A to B and then add B to C, we will end up starting at A and ending at C. So now given this information that we have, we can say, well, A to B as a column vector is 4, 7, -3. And B to C as a column vector is -1, 2, -5. If I just add those together, I'm going to find A to C. Another thing to notice here when we're adding, if we want to go from A to C, do we notice that those two letters are the same when you're adding two vectors together? Because you went to A to B, now you're at B. Where are you going from there? You're going from B to C. Now sometimes we can mix things up a little bit, and we'll see that in some of the geometrical proofs we'll do later, but this is the starting point. You're always connecting letters as you go along. So here's one for you to try. Again, I'd suggest drawing the diagram first to get a sense of what you need to do. And this is in 3 dimensions. So notice that AC has no J. So that'll be a 0 in there when you make that column vector. So here's a picture of what's happening. You want to find B to C, and you know A to B and A to C. So B to C is the same as going from B to A and then A to C. And here, well, we don't know B to A, but we know A to B, and we know that B to A is just the negative of A to B. So then when you put things in, you can take that first column vector, multiply it by a negative, add A to C, and you'll get your final vector. What's that? Okay. Yeah, and there, depending on how you looked at it, you might have set up your equation differently, but you would still, again, the diagram, as long as you're making an equation from your diagram that makes sense, then you're going to be able to figure that out. So other people might have said, did you set it up this way? A to B plus B to C equals A to C?
No, I did AC
Yeah, and then you would subtract that on the other side to make it work. And you can work with vectors like an equation like that as well. Now, you had this here sometimes if what we're going to find is you're going to be given A, B, and C as position vectors from O. Remember how position vectors work? So then if you had position vectors, B to C would be the same thing as going negative B plus C if you had position vectors. And so there's another way of looking at it. We didn't have the position vectors at this point, but we will be doing a lot of stuff with position vectors coming up. Okay, and the very important zero vector, which can be written with a 0 with an arrow over top of it. Sometimes you can go all the way around, add a bunch of vectors up, and end right back at the same place that you started. So you haven't moved whatsoever. Like here, if I go from P to Q, then Q to R, then R back to P, my start and end point is exactly the same. How do we show that? Well, that would be a 0 vector. In 2 dimensions, you'd have 0, 0. 3 dimensions, 0, 0, 0. Can only imagine what it would look like in 5 dimensions. Just a bunch of zeros. So that is our 0 vector.